Okay, so today I will present you the experiment of the group of Shai and Yenak from 2014 about validate that the Anderson localization in matter depends only in one parameter, which is the parameter the scale between the length of the system and the length of the localization, the difference between them. Okay, I will start. Anderson localization describes the wave scattering inside the medium, and single parameter scaling theory predict that in deep localization, all of physics simplified into one ratio, which is the between the system length and the localization length. And we want to see that after many times of measuring the system, the transmission of the system, the transmission distribute like a Gaussian.
What do you mean many
like
times?
that.
When you say many times, it doesn't change with time, yes? It doesn't change with time. The system doesn't change with time.
Between one measure and another, we change the system.
Okay.
We're changing
From
the geometry of the system.
Realization.
Yeah. So our language, our parameters will be the transmittance, the intensity of a wave that come inside the system and go outside. We're measuring what's come inside and what's go outside the system. The ln of t, we are predicting that the ln of t is distributed like Gaussian, not t, but ln of t. And the control ratio, we will define between a small control ratio and big control ratio, and participant numbers, the effective number of open transmission channels. Because if we have a tube and we produce waves from inside the tubes to the outside, the wave can move through a lot of channels. So also in our experiment, in the localization area, in the localization regime, these channels drop to 1. There are only one channels to go inside and go outside the system. So the system itself, it's tube. I needed to tell you this earlier, but it's a copper tube, which inside the copper tube there is a lot of aluminum balls with their own refractive number of 3.14. And we make one measure. And before the second measure, we rotate and mix the tube, so the balls will inside the tube will arrange differently from time to time. And we're making this. We're making that few dozens, if not hundreds, of times of measurements. We're measuring the transmission matrix and repeat it after we rotate and vibrate the copper tube, and make it again a few dozens or 100 times. Okay, this is the first results. This results is for only one measuring. It's not for the whole measuring of the system. But the red graphs is for a length ratio of 1.7, and the size of the tube is 40 centimeter, and the green one is for a length of 102 centimeter, and the length is in the length ratio it's much bigger. We can see the first graphs are the intensity of the wave come inside from A point and go outside from B point. This is for one point to another point, and the graph B and E are from A point, and we are averaging all the B points of the exit. And what's the important one is C and F, and which we are taking one point A and we are averaging it all over B points, and then we are averaging all over A points. So we get the transmittance matrix to this section, and we can see the differences between the long tube and the short tube. We can see this spectrum is much more discrete in the long tube, in far more of the localization area, and there is only a few or discrete frequencies that are coming outside the system. Here it's not discrete, it's maruach, spread all over the medium of the frequencies. I will get this in the end. And the mechanism of the channels, the number of channels is defined by the eigenvalues of the transmittance matrix. You can see in a diffusive regime there is a lot of channels to go through the tube, and when it localized, there is only one channel that can go inside and outside the tube. Okay, what we can see here, all of these are single measurements, and we can see that M goes to 1 from each of every measurement, and we can see here that as long the transmission got bigger to 1, M is also dropping to 1. This is this size is for the long tube, where we are in the localization ratio is big. It's almost 4. Here the localization ratio is almost 1. So the channels, the average of the channels is not 1, it's bigger than 1. And here, in the long tube, the channels are almost 1.
You mean the channels are almost 1? How do you read this plot here? Transmission. The transmission is 1.
So the averaging channels is also 1.
So M should be 1 when it's localized, right?
Yes, yes,
So
M should be 1.
Okay, most of the channels are 1.
Yeah. Okay, after one measuring, after we calculate all the transmittance, and we are plotting the matrix of the transmittance, we sum up all the eigenvalues of the matrix, and then we are measuring it for the whole dozens and hundreds of measurements that I make for this experiment. I remind you, we are measuring in one form of the tube. We get from this the matrix and the eigenvalues of the matrix, and then we mix the tube again and measure again, and we get another matrix with another eigenvalues. That's we came here. We can see in the region of deep localization I didn't define G, but G depends on the localization ratio. This is the graph of the long tube where the localization is deep, and we can see after averaging all the possible outcomes and make a logarithmic scale, the distribution become really like a Gaussian. And in the default regime, where I didn't write it here, the localization ratio is very small. It's 1 or 1.7. We don't get a Gaussian. We see a rise like a Gaussian and then cut off and then drop to 0. It's explained. They're explaining it in a different article. So I didn't get deep inside it. For the explanation why it's not a continuous Gaussian and have a cutoff. But we can see in deep localization the behavior like a Gaussian. The transmission distribute like a Gaussian. We can also see here we have a graph of the localization ratio, and in circles we have circles, crosses, and squares. The crosses are the average number of active channels, and the square are the inverse of the active channels. And the circles they are used to validate single parameter scaling theory, the statistical ratio. But we can see here in this regime they are all scattered, but when the localization lengths go in the region of 4, like in this graph, the green graph here is the system is long enough. The ratio is בערך 4-ish. We can see also here when it's close to 4, they are all coming to 1. Or the average of the effective number of channels and is inverse. They are all coming to 1. For conclusion, in the right ratio of scaling between L and the localization lengths, in the right ratio, the statistics of the distribution of the ln of the transmission is fit like a Gaussian, and we also proved the single parameter scaling of this ratio, and also proved that in localization mode, in deep localization, there is only there is only one channel to go through inside the matter. And that's it.
Okay.
Question?
So, if it's not in the localized regime, so what do you expect for the channels?
I expect more channels than one. I don't know to tell you how much channels, but it won't be one.
What should be the distribution?
The distribution is here. We saw the distribution starting like Gaussian and then...
No, the distribution of channels.
Oh, channels.
Yeah.
I know that it's higher than 1. They didn't talk about it about the distributions in the article.
You mean larger than 1?
Hmm?
Oh, you mean in the localized regime?
In the localized regime, it's
yeah,
1.
Only 1. So you get more. Okay, you get more channels. Okay. So that's open channels, right?
Yes.
Okay. Open channels means channel that guide all the energy from one end to the other. They should be more than 1. Okay.
Yeah, it should be more than 1. They don't say how much and why in the article, but I can look for it, check it out.
And do they say anything about it? Does it correspond to a localized state inside the system? So you see when you showed the spectrum, it was like you said, it's like a discrete spectrum, okay?
Of
At the beginning,
here?
yeah, here.
Okay.
When you show the spectrum here, it looks like discrete. So when you get an open channel, it corresponds to a mode like that, to a peak. It's a question.
Yeah, I understand. If the channeling is correspond to specific frequency, this is the question.
Yeah. So for one frequency, I mean, so for certain frequencies, you see a peak. Okay, so that means that the transmission is strong for the.
Yeah, for this frequency.
So is the channel, the open channel, correspond to the excitation of that mode, that particular mode? And it's only one at a time, you see, it's because it's a discrete spectrum.
Yeah.
Whatever the frequency is, it's one. I mean, it's one peak. You don't have more than one peak.
Yes.
While on the other side, on the red plots,
because we are not in the localization regime, and there is a lot of channels to go for
and participate to the transmission.
Yeah,
right.
It's I forgot the English for the Nimrach. The frequencies are
continuous. No?
Yeah, in continuous limit, not a discrete limit.
Right. And if you remember the movie, I show you the output of the tube. Yeah. Before localization, it was the speckle was changing like smoothly, continuously, and when we reached the localized regime, it was like frozen on one image, then changing image. Yeah. I guess this is exactly
it's becoming discrete.
Yeah, so these are actually the channels that you see. One channel is transmitting, then another one, depending on the frequency.
They don't speak about
the mode of the system.
Yes, this mode. They don't speak about it in the article between the channels and the frequencies. If there is one channel for one frequency, I can look it up. Any other questions?
Other questions? It's not an easy paper.
No, it's not
many concepts that you have to explain.
Yeah. There is a lot of new parameters for me and new methods for me. I read a lot in the last week. I read a lot.
I see that you understood.
Yeah.
Very good. Any question about the one parameter scaling? They demonstrated or they confirmed what is the idea here? They show that when you are in the localized. So what is the parameter? What is the
how they measure all the parameters?
What is the single parameter scaling means here? How do you understand that here?
In general, when they talk about the single parameter, they talk about the length ratio. That he is deciding about if there is localization or there is no localization in this medium. Right. And we can see in the right regime of this ratio, the green dash, all the other the important parameter. For example, this is example for the important parameter of m, which is need to be 1. They are calculated. They measure it and calculate it, and it's converged to 1, towards 1.
And that tells you that this is single parameter scaling? I don't see. You remember this plot where we plotted the log of the conductance as a function of the size of the system?
Sure.
And there was like 1D, 2D, 3D.
Yes.
3 lines.
The simulation you showed us.
No, not simulation. That's the theory, the scaling theory of localization. And single parameter scaling means that the log of G depends only on the length of the system. Okay, so this is a scaling, so it means that.
Yeah, it's like the log of T here is
right.
distributed differently for
the idea was
different.
That as you increase the size of your system, okay,
yeah,
1D, 2D, 3D, when you increase it,
when you increase the size, the distribution of T or G of the conductance.
Yeah, does it decreases or increasing? It increases.
It became like Gaussian.
Not the distribution, the value of the conductance itself.
The value.
The conductance, how does the conductance depends with the length of the sample. So when it's 1D or 2D, you are always localized. So as you increase the size of your system, the conductance decreases because you cannot go through. Okay.
Decrease and the energy got trapped inside.
Right. Yes. But when in 3D, there was like how do you call that? There was like mobility age. Okay. Before that mobility age, you are always diffusive, so the conductance increases with the size of the system. Yeah. Beyond that, you are localized, and then it decreases. So they don't make a connection with that. I don't see a direct connection with that. They claim that
I don't remember they do. Maybe I really read all the article, and I don't remember that they are connecting it. I don't think they are connecting.
No, because they call that single parameter scaling prediction, so it should be.
The single parameter that they are discuss about is the length of it.
Yeah,
that he is deciding if there
that's
is
correct. That's exactly the parameter in the scaling to focalization. But okay, they show that when you are localized, everything collapses on one line. But the theory of the scaling theory of localization is for all the regimes, from diffusive to localized, from small length to large length.
Yeah.
So I have to look at that in detail and understand how the dashed line is the prediction of SPS. Okay. Only for large R.
Yeah.
Okay, maybe only for large R. Okay.
Yeah. This regime is large. It's large. And all the other parameters are converging to this regime.
Okay, thanks a lot.
Thank you. Laboratoire, toujours?
Who's next?
So who is next? In my
I can be next.
In my list.
לא, עושה אבל רק צריך את הסוף
I'm sure that you showed you made them
the pictures, yes.
The tube, the first picture of the tube,
Yeah,
the board inside.
Oh, yeah.
That's very nice.
Yeah.
I will send that to Azigenak. It's my colleague, so we.
You're collecting the picture? I will send it.
Yeah, send me the presentation. I didn't receive the presentation, all the presentation from last week. Can you send me?
Yes.
כן, כבר שלחתי.
You send me. Yes, yes. He's always looking for nice picture. But
Yeah. Yes, it's חוסך המון זמן.
but it looks realistic, very realistic.
Yeah. במקום לשבור את הראש ולהכין בעצמי.
Correct?
How do I change it to be
Wait.
to my Oh, see.
להוריד מחשב נייד,
כן, צריך ללחוץ על הכפתור.
יוצאים ונכנסים אליי.
Okay. Okay. Wait. So just a moment. No, how do I go back? Okay. Okay, so good afternoon, everyone. So today I want to talk about how we see, or rather how we predict, where waves will go in a messy environment. So, chaos. In our course and in much of condensed matter physics, we deal with disorder. So whether it's light scattering through a turbid medium or an electron moving through a dirty semiconductor, we usually model the environment like this image here on the left. So this is a random potential. It's chaotic, it's noisy. If I asked you to look at this random noise and point to exactly where a wave would get stuck or localized, you couldn't do it. Historically, we've relied on complex numerical simulations or statistical averages to understand phenomena like Anderson localization. Okay. So, but what if chaos was actually hiding a map? So the paper I'm presenting today by Philoshe and my brother, correct me if I'm wrong in pronouncing the names, argues that there is a hidden deterministic landscape underlying that random potential. So this is the chaotic potential, and this is the hidden landscape, which we will talk about. So look at this image on the right. This is the exact same system as the left, but viewed through a new mathematical lens, a function they call U. Suddenly, the chaos disappears, and we see a clean network of valleys and boundaries. So, this paper proposes that these blue lines you see aren't just pretty geometry. They are physical walls. They predict exactly where waves will be confined, and they do it for any type of wave. So, quantum, acoustic, or electromagnetic. So, my presentation today is titled Unveiling the Hidden Landscape, and I'm going to show you how we can mathematically turn the chaos on the left into the map on the right. Okay. So, before we look at how they solve this, let's establish exactly why this has been such a persistent problem in physics. So, we generally categorize wave confinement into two buckets. First, we have Anderson localization, which is what happens in the presence of strong disorder, like the potential we saw earlier here. So, this leads to exponentially localized states. Second, we have weak localization, which is usually driven by the geometry of the domain itself. For 50 years, we've treated these phenomena using statistics. So we can predict the probability of transmission or the average conductance of a material. But here's the catch. We are terrible at predicting the behavior of a specific single realization. So look at this comparison. On the left, we have the specific random potential, V of x. It's this one that we've seen. And on the right, we have the actual quantum states, the eigenmodes that live in that potential. It's these ones, the delta peaks. So if you look closely, the shapes of these modes do not simply match the deep wells of the potential. You cannot look at the left image and intuitively draw the shapes on the right. The relationship is non-local and complex. To find the image on the right, we traditionally have to solve the full eigenvalue problem, which is this one. If you can see, I think there is a bit of light in here. That is computationally heavy, and more importantly, it doesn't give us physical intuition. It gives us the answer, but it doesn't explain the mechanism. So this paper bridges that gap. It claims that Anderson-weak localization are actually the same mechanism, and it gives us a way to predict these modes and these mode shapes without solving the Schrödinger equation in here. Okay. So this brings us to the core innovation of Philoche and Mayboroda's work. They asked, is there a simpler mathematical object that encodes the geometry of localization without solving for every single quantum state? The answer is yes. They call it the landscape function, denoted as U. So this is U. Okay. So instead of struggling with complex eigenvalue problem, which requires finding specific energies E and specific states psi, they propose solving this surprisingly simple Dirichlet problem. L acting on U equals to 1. This exact equation. So here L is our wave operator. It's the same Hamiltonian with the same random potential we saw in the previous slide. But mathematically, this is a massive simplification. You know, we are moving from a complex eigenvalue problem to a standard linear system. We're just solving for the response of the system to a constant right-hand side. So, as you can see. So, what does this function U actually represent? So, think of it physically. Imagine our disordered system is a flexible membrane. The operator L describes the stiffness and the structure of that membrane. If we were to apply a uniform pressure, like a constant load, across the entire surface, the membrane would deform. So the image you see here is that deformation. This is the landscape U of X. So notice that while the original potential V was jagged and random, U is smoother. It has structure. It creates a terrain of high peaks and interconnected valleys. Now, the authors of this paper, key insight was that this landscape, specifically the network of valleys you see in here, is what actually confines the waves. So the waves don't just get stuck in the deep wells of the random potential, they get trapped in the valleys of this landscape function. So we have effectively transformed a problem of randomness into a problem of geometry. Now let's see how well this geometry actually predicts the physics. Okay. So, okay. So, we have this landscape function U. It maps out the domain nicely, but as physicists we have to ask, why? Why would the probability amplitude of a quantum state care about this specific mathematical deformation? Why? So here I will answer this question. This is actually the mathematical engine of the paper. you can see. So the authors of this paper, they derive what I like to call a magic inequality. It states that for any eigenmode psi with energy E, the amplitude is strictly bounded by the landscape function. So, think of it physically. The function u of x acts as a variable ceiling for the wave. But to really understand the power of this ceiling, we need to look at this figure 4, from the paper. These are the log plots. These aren't just your standard 3D plots. These are logarithmic plots of the wave amplitude. It's a map. This is crucial because it allows us to see the invisible walls clearly. The black lines you see traced over the terrain are the valleys of U, the places where the ceiling drops low. So, look at the darker red center. This is where the wave lives. Now, watch what happens when the wave attempts to cross one of those black valley lines. The color shifts instantly from red to yellow to blue, like that. So, now here's the mechanism for those interested in the connection to Anderson localization. The authors found that this is not just a gentle decrease. Every time the wave crosses a valley defined by U, its amplitude doesn't just dip, it gets crushed by roughly an order of magnitude. Because the landscape is a complex network, the wave has to run a gauntlet of these valleys to escape. One drop, then another drop, then another. So this sequence of force drops is exactly what generates the exponential decay characteristic of Anderson localization. But look back at the inequality here. The factor E is still there. This tells us that the walls are not just absolute for everyone. A particle with higher energy E raises the ceiling, allowing it to breach shallower valleys that would trap a lower energy particle. So this inequality proves that localization is not just random. It's the result of the landscape function U, literally forcing the wave to vanish behind these barriers.
So is it this picture is U or is it E times U? The picture that you have here.
Yeah, so this is these are the log plots. It's
No, for the field, right? But the network that you draw here. It's U of x, or it's E times U.
it's E times U of x. Here,
Yeah, because I see some broken lines, so it seems that it depends on U.
yeah.
On E, sorry, on the field.
Yeah, it does. This is what we see, the difference here between the modes, the mode 5 and mode 8. You can see the logarithmic nature of that.
Yes.
So, yeah, exactly. So, okay. So, we have established that the landscape function U creates invisible walls, but we know from basic physics and from the course we are taking that not all waves are trapped forever. High energy electrons conduct, high frequency light can transmit. So how does this theory account for that? This is where the magic inequality we just saw becomes dynamic. So, if you can remember, this is the inequality, the magic inequality. Look at the term E. It acts as a scaling factor. So physically you can think of the landscape U as a fixed terrain of mountains and valleys, as we've seen. So the term 1 over E acts like a water level relative to that terrain. I will show you in a moment. So look at this top row of figure 3 from the paper. So when the energy E is low, the water level is low. We can think of it like that. So the effective valley network, which is the set of points where the wave is allowed to live, is dense and fully connected. Look at these top modes. The black lines, which are the valley boundaries, are thick and unbroken. The waves are strictly imprisoned in single cells. They cannot cross the ridges. This is strong localization. Now, please look at these. But watch what happens as we turn up the energy dial. As E increases, the condition that U is smaller than 1 over E becomes harder to satisfy. Effectively, the walls start to shrink. So, look at mode 45 or 70. This is mode 45, this is mode 70. It's behind me here. So, do you see those small gaps opening up in the black lines? The barriers are being breached. The wave, which was previously trapped in one cell, effectively spills over into the neighbor. So the distinct paddles of probability start to merge into lakes. Now look at the bottom. I think it's cut off because of this, but you can see these three modes: mode 98, 99, and 100. So near mode 100, you can see that the network has disintegrated. The walls are now just isolated pillars or peaks that the wave washes right around. The subregions have merged completely, creating a path that spans the entire system. This is, I think, the most beautiful insight of the paper. The transition from an insulator, like localized, to a conductor, delocalized. So it's not a mysterious quantum breakdown. It is a percolation transition. We don't need to solve the Schrödinger equation to find the transition energy. We just need to look at the geometry of U and ask, at what height do the valleys connect? So Philo, Shem, and Moroder have effectively turned the complex wave physics problem into a geometrical map reading problem. And this brings us onto the next slide, which I want to show you. I tried to generate a nice analogy of the percolation and what I just explained. So you can see this is a 3D plot of the valleys and the peaks, and this is the water level, which is how we can isolate those peaks, and you can see how we can actually map this out and deal with the chaos. And I also tried to show a little animation, but
Just one point which is important to say is that for the Schrödinger equation, localization is for low value of E of the energy. So for E equals 0, but as you increase energy, then you start to be delocalized. So that's what they show here. So this is not the wave function, it's the Schrödinger equation. So as you increase E, you increase the level of the C here.
exactly.
And the domain becomes larger and larger, and the wave becomes delocalized.
Exactly. This is why we get the peaks of energy.
Can you apply the video again?
Yeah. Great. See, this is what happens when E increases. But okay. So this brings us to the strongest claim of the paper, unification. So usually in condensed matter physics, we treat weak localization and Anderson localization as distinct phenomena with different theoretical treatments. You know, weak localization is often framed as an interference correction, while Anderson localization is the complete halting of diffusion due to disorder. But Again, Filoche and Mayroda argue that they are actually the same mechanism, observed at different scales. So I tried to generate a simplification of what we've seen before. So we could see the different regions. I mean, how it looks. You have a very sharp contrast here. It's not organic, of course. It's not like the real plot from the paper, but it's a good simplification to understand the concept. So look at this logarithmic plot. Inside this central cell, the wave amplitude is high and relatively uniform. It is trapped in a single basin of our landscape function U. This confinement in a single subregion is what we identify as wave localization. The wave is weakly coupled to its neighbors, but mostly lives here. So, now what happens if we zoom out? To move away from this center, the wave has to cross these valley lines, the walls of the landscape. Because of the inequality we discussed earlier, every time the wave crosses a valley, it pays a penalty, you could call it that. The authors found that crossing a valley reduces the amplitude by a roughly constant factor, essentially dropping by an order of magnitude. So this is the aha moment, you could say. If you have to cross 10 walls, and each wall cuts your amplitude by half, you don't get a linear decrease. You get a multiplicative decrease. Like a multiplication, like Vegab. Mathematically, a sequence of constant multiplicative drops over a distance is exponential decay. It's e to the minus. So Anderson localization is simply the macroscopic emergence of successive weak localizations. It's not a magic switch that flips. It's the result of a wave running a gauntlet of these geometric barriers. This is why they call the mechanism universal. It doesn't matter if the disorder comes from a random potential, like in electron transport, or from the complex shape of a cavity, like in acoustics. If you can calculate the landscape U, you can predict the decay. So far, we have focused heavily on the Schrödinger equation and random potentials, which is the standard context for Anderson localization. But the most powerful aspect of Filoche and Mayroda's theory is its universality. Remember the defining equation. The operator L on U equals to 1. Nowhere in that equation does it say this must be a quantum particle. It simply requires L to be an elliptic operator. This means the theory applies to almost any vibrating system in nature. So, if we use the standard, say, Laplacian, this describes acoustic waves in a room or the vibration of a drumhead. If you use the bi-Laplacian, a fourth-order operator, it describes the vibration of rigid thin plates. But for us, in this course on light through turbid media, this third point is crucial. When we study light in disordered media, we're dealing with spatially varying dielectric constants. So mathematically, this changes the operator to a divergence form. Localized changes in the medium's refractive index act just like the random potential in the quantum case. This means we can theoretically take a map of a turbid medium's disorder, calculate the simple landscape function U, and predict exactly where optical hotspots or localized light modes will appear. So, to prove this universality, the authors stepped away from random potentials entirely. Look at the images on this screen here. So, they created a complex domain, a room with a bottleneck, some blocked points, and a sharp track. There is no random disorder here, meaning that V is equal to 0, the potential. The disorder is entirely in the geometry of the walls. You can see here, the landscape U is calculated for this shape. Even without random potential, the geometry itself creates valleys, those red lines. So here you can see the actual vibrational modes. Just as we saw with the quantum electrons, the classical vibrations are trapped exactly within the partitions created by the landscape. So, whether it is an electron in a semiconductor or a sound wave in a concert hall or even a photon in a turbid cloud, the mechanism is the same. The system reads the landscape view, and the values tell the wave where it is allowed to live. So, what is the take-home message of this paper? If we boil it all down, Philosh and Boroda have taught us that randomness is just geometry in disguise. So, we started with a complex problem, predicting where a wave will go in a disordered system. Historically, this required brute force number crunching to solve the eigenvalue problem. A lot of computation. But this paper gives us a shortcut by solving the much simpler linear equation, L acting on U equals to 1. We generate a map, as we've seen. So, we learned that this map, the landscape U, dictates the physics through a fundamental inequality. The wave amplitude is bounded by the energy times the landscape. It's the plot that we've seen with the log of the modes. It was mode 5 and mode 8. So, if the landscape dips into a valley, the wave must vanish. If the valleys are deep and numerous, like in Anderson localization, the wave is trapped exponentially. If the valleys connect, as energy increases, the wave percolates and the material becomes a conductor. So, the impact of this is massive. We no longer have to simulate a billion random photons to guess where the light will get stuck. We can just calculate the landscape once and know the confining regions immediately. We have effectively replaced a probabilistic guess with a deterministic map. So, this leads us to the future. So, the authors suggest that if we can understand the map, we can rewrite it. So, instead of just analyzing random media, we can start designing it. Like, imagine engineering a material with a specific valley network to trap sound in a precise location, or to confine light in a laser cavity without mirrors. This is the concept of inverse design, and this landscape theory is the tool that makes it possible. Finally, bringing it back to our course on light through turbid media, when we talk about light struggling to pass through a cloudy, disordered medium, we usually talk about scattering mean-free paths, or diffusion, as we've seen. So, this paper just offers a different perspective. It suggests that inside that turbid medium, there is a hidden, calculable landscape of refractive indices. The light is not just bouncing randomly, it is flowing through the valleys of that medium. If we want to truly master the control of light in complex media, we need to stop looking at the noise and start looking at the landscape. Thank you.
Okay, so what you showed here was for 2 dimensions.
Yeah.
2-dimensional system. What about 3 dimensions? Is there a landscape like that in 3 dimensions?
Well, so, I mean, this is what they explain in the paper about the 2 dimensions. About 3 dimensions or more.
Do they have any results in 3D?
It's a good question.
Because in 2D we know it's always localized. It's a question of size of the system.
Yeah.
In 3D there is this crossover. So I don't know how the theory will describe the mobility edge in that case.
Like in
where the disorder, the level of disorder will change the nature of the landscape.
Yeah, that is a very good point. Yeah, and I also wanted to show you, I wrote a little simulation. Let me show you. I tried to write some Python code. I think it's better than something that's AI generated. Here you can see what we've talked about, and you can see the eigenmodes.
Wow. So that's the landscape of what you have at the beginning. The beginning is the potential, random potential.
Yes.
So that's the random potential, right?
Yeah.
Okay. And here you build the landscape.
Yep. Exactly.
So how do you do that? What did you do exactly in the simulation? Or is it a simulation? Is it just AI's AI?
No, it's a simulation, but
So what you solve the LU = 1 equation?
yeah. I mean, I made it a while ago, but I have the code here. I could show you later. And also I wanted to show you, how the map looks. So this is the random potential. It's very noisy. This is what happens. We have the landscape function u of x in the value network, and you apply L equals to 1, and you get the eigenmode confinement, or magic inequality, and you could see the eigenmodes. It's not perfect, but it's the best. Okay.
So actually we demonstrated this theory in an experiment. We were able to measure the landscape with elastic waves and to confirm that the modes are localized in the valleys of the landscape. But we never published this work.
Oh, well, it's a shame.
Yeah.
You should.
Yeah, that's the problem when students they leave and it's hard to finish the work. Yeah, so it's very nice. So I mean, these people, they are mathematicians actually.
Yeah.
And they're really, I mean, their theory is very simple. Nobody thought about that before. I mean, there are a lot of theory on localization from the mathematical point of view. Very long demonstration that 1D is always localized. And, you know, the mathematical approach, you know, with all the condition and but this theory is new and nobody thought about that. So it's really a real breakthrough in the field.
Yeah.
And you're right that the idea is to consider one system. What is one system localized? Or what was previously discussed by Oya is statistical approach, where you look at statistical quantities like transmission, and here it's for a single configuration.
And it uses the.
I mean, you can look at the theory. It's not difficult to demonstrate.
Yeah, it uses the
green function.
The green function. Yeah, exactly.
Yes, don't worry. We'll come back to me.
Okay.
Yes, don't worry.
Okay. Thank you.
Okay. Thanks. Any question? Any question?
Questions?
Okay, so we make a small break.
Hello everyone. The topic I'm presenting is cavity quantum electrodynamics with Anderson localization modes. In today's quantum technology, there is a big challenge. The challenge is how to enhance the interaction between single photons and single quantum emitters. To get this objective, we need a highly engineered optical cavities, but the cavities always have many imperfections, and the cavities are very sensitive to these imperfections. These imperfections could be seen as many disorders. So how to solve these disorders? This paper give us a solution. The solution is to let these disorders be used as a resource. As a resource which could be generated as strongly confined Anderson localization cavity modes. So what's the Anderson localization? Anderson localization is when the system have big disorders. The light will be scattered and then they will have this destructive interference. And then they can't go through the system. They are trapping. This energy are trapped in a certain region. This is Anderson localization. And this work is combine Anderson localization with the photonic crystal. In the left picture, this is a photonic crystal. The crystal is two dimension, and you can see there are many holes in the crystal. Each hole could be same as a scatter. When light go through, when they go through, they touch these holes, they will be scattered. And we can see in this crystal, in the middle of the crystal, there is no hole here, so the light can go through this path. It's like a waveguide. The light can't go left or go right because they will be scattered. The light only can go through along this path. So how to combine the photonic crystal and the Anderson localization? The Anderson localization, the core of Anderson localization is disorder. So we should make a disorder on this of this crystal. The red circle is the standard position of the horse. But we can see they have some disturb. They have some difference. This is the disorder we made. This is the disorder we made. So now we get a photonic crystal with disorder. With this disorder, the light we will get some region. In their region, the Anderson localization will happen. Next we will see if Anderson localization happen in the crystal we made. How to see the Anderson localization? We scan the crystal and we will get its spectrum. This spectrum is get at the temperature of 10 and degree of disorder 3%. Degree of disorder is the difference of the horse position to the standardization of. So in this condition, what we get? We get the spectrum like this. The x-axis axis is wavelength, the y-axis is position, and the z-axis is the intensity. So we get many peaks. These peaks are separate. This is the proof of Anderson localization. And we can see the position. This position is along the path. So if there is no Anderson, Anderson localization, we will get the most light will go through the path. We won't get so many peaks. And in the right picture, we calculate the data we get. We will get a picture like this. On the dotted line is the Rayleigh distribution. The Rayleigh distribution is of the position without Anderson location, and the blue circle is our experiment consequence. We can see they have big difference, and we calculate the variance of them. We will get 5.3. And for standard, if this number is less than 2.33, we can think that the Anderson localization happened. So with both consequences, we made a crystal which Anderson localization could happen. And then we had to get Anderson localization. What's the relationship between Anderson localization and the degree of disorder? This is the experimental consequence. The x-axis is of wavelength. The y-axis is the intensity, and each line of different degree of disorder. We can see the lower one is with no disorder. We can see there are nearly no peaks. So almost almost all lines go through straightly. They not be trapped. But when we increase the disorder, the light are trapped. So we get so many peaks, and with the increase of degree, we can see the intensity of the intensity is increased too. So if we increase the decrease of disorder, the Anderson localization will be enhanced too.
How do you see Anderson localization? How do you see the Anderson localization? What tells you that this is?
Here each peak represents Anderson localized mode. Yes. So these peaks represents the intensity of these modes. We can see with the increase of the degree, the intensity of modes are increased. So the Anderson localization is enhanced. And then we want to get the resonation. but the resonation is to let the frequency of the quantum dots agree with the Anderson localized cavity. But how to do this? First, we see this spectrum. The QD is quantum dots. We measure 3 quantum dots, and the C1 and the C2 are Anderson localized cavities. Cavities we can see when the quantum dots get close to the cavity mode, the intensity is large. So when they get the same number, we will get the maximum intensity. They get resonance, and then see the picture B. See the picture B. This is they will change the position of the quantum dot, and the cavity mode will change with the change of temperature. We can see when temperature increase, their position are go to right, and we will see that their moving rate is different. The moving of these quantum dots are quick, but the moving of these Anderson mode is slow. They have different rates, so we can change temperature to let the quantum dot and Anderson code get the same position. Yeah. So this is the temperature turning. This is a turning independent on their different independence of temperature. And then we can separate the quantum dot 5 from here. We will get a temperature of quantum dot 5 and Anderson code 1. It's like that. We can see this is they are different. They are with different temperature, and the x-axis is wavelength, the y-axis is intensity. But with the increase of temperature, we can see the position of quantum 5 is changed. Is go to right, and the position of Anderson code is go to right too. But the rapid of the moving of quantum dot 5 is more fast. So we can let them get resonation by changing temperature. Here they get a resonation. Yeah. So we can turn in to get a resonation by change temperature. Yeah. We can get the coupling of a single quantum dot with a single Anderson mode. This is very useful. And at last we will see. At last we will see the decay of their quantum dot. The red one is the resonation is the quantum dot with resonance.
Resonance, you mean
Yeah.
resonance.
Yeah, it's like this. Yeah, with resonance. And the black one is without resonance, like this one. Yeah. We can see they have big difference. They have difference. With the time, the decay of the red one is faster. Actually, with their calculations, the decay rate intensity of the red resonant quantum dot, the red one is approximately 15 minutes of that of non-resonant ones. Is a big difference. And in picture B, we can see this is the tuning. The tuning is the difference of the center frequency, center wavelength, and the center wavelength of quantum dot and the wavelength of the Anderson code. In this position, it's a resonance position, but when the tuning increase, we can see the decay rate decrease very quickly. The red one is of quantum dot 5. The blue one is of quantum dot 6. This is 5. This is 6. Yeah. And the blue line is of the Anderson mode. It's not symmetry. This is because it's not only one Anderson mode. It's two. It's two mode. It's two mode, C1 and C2. So it's not a symmetry. It's not symmetry. And in picture C, we will see the condition in large detuning. With the detuning increase, we can see the decay rate is decrease. In picture B, the Purcell effect dominates because the dominating is the coupling of the point and point of the quantum dot and the Anderson code. But in large detuning, the Purcell effect is very low. So the domination is the slow light coupling. When the quantum dots are out of the resonance with the Anderson localized cavity, they may couple with the slow light mode of the photonic crystal waveguide. Yes, so the red line is the slow light, is of the slow light effect. So to conclusion, we want to solve this problem. We want to enhance the interaction between the light and the materials. So we want to make Anderson localization region in the crystal, and then they make this materials, and they get Anderson localization, and then they find the Anderson localization intensity, the relationship of the Anderson localization of the degree of disorder and the temperature, and they can tune in the quantum dot and the Anderson code by the temperature. This is a big work to help us to enhance the interaction between the light and the materials. Yeah, that's all. Thank you.
Thanks a lot. Questions? Many questions.
I like how it's connected 3 times in a row. Anderson localization 3 times in a row.
What is your question?
All the papers on Anderson.
Yes, everyone is interested in that. Can you explain the experiment? Okay, to show the modes. The first pic, the next one here, this picture. How do they get this measurement here? Position, wavelength, and intensity as function of position and wavelength. How do they get this measurement? What is the experiment like?
Experiment like the and there are many quantum dots inside the materials.
Okay, so
yeah.
that you didn't say.
Yeah.
You didn't say. Okay.
They distribute randomly, and here is along the path. They will let the quantum dot to emit and measure the spectrum like this. Yeah.
So this spectrum is the result of what? Experimentally, how do you measure that? So you do with the spectrometer, you do some spectrometry of your system. The system is, how do you excite the quantum dots? Just technically, how do you realize this experiment? Do you have?
Just the matter is the spectrum, and
those quantum. So you have many quantum dots. What is the quantum dot, by the way? What is the quantum dot?
Yeah. Here we can see some quantum dots. Quantum dots have different scales, and they can emit energy because and they can emit energy with different wavelengths due to their different scales. Yeah.
They have different what?
Different wavelengths.
No, they emit different wavelengths due to their different size. You said different.
Yes.
Geometry.
Yes. The energy, the wavelength of energy they emitted is related to their scales and positions, and maybe some other elements is random. They just want to get the quantum dots which can emit different wavelengths of energy.
Okay, so how do you excite them?
Excite.
Excitation, right?
They just put these dots inside the metals to.
No, okay, but
yeah.
to get photoluminescence, to get emission from these quantum dots, you need to excite them, right? So there is probably a source. They are shining some source on the sample, or no, you don't have the details. They don't give the details of the experiment, maybe. They should.
Yeah.
And can you explain what is the Purcell factor? What do you mean by Purcell factor?
Percent factor?
What is the Purcell factor?
Where?
Purcell? No. After that. I think after. Yeah, after that. After the next one.
In factor?
Purcell. P-U-R-C-E-L. Go next. Okay, here. The figure B is Purcell effect. Oh, sorry, Purcell effect.
Purcell effect.
Oh, yeah. So can you explain this effect?
Purcell effect is the coupling of two position of 2 points, and the efficiency of Purcell effect is related to the Q quality and the volume. Yeah, and the Q.
So the idea of the Purcell effect is that you have a resonator.
Yes.
And you have a source. So what is predicted is that the source will, the presence of the resonator will enhance the emission of the source. You get much more light because of this resonant effect with the resonator. So this is related to quantum electrodynamics. I don't know if you get any course on that, quantum electrodynamics? No? So that's the interaction of a source with a resonator. So you have an atom that can emit, and so without any other source, it will have some emission. You put it in a resonator. So here the resonator is the localized state, okay? And you see an enhancement. So you see this peak, this red peak here of decay rate. Okay, so that's the emission due to the coupling between the source and the resonator, the mode here. That's the main result of the paper.
Thank you.
Okay, thanks a lot. Very nice. It's a very nice paper, very nice presentation. So who is next? Can you help? This paper?
No,
Yeah.
that's okay.
I'm not sure some the experiment, the detail of the experiment.
Hello everyone. Today I will introduce the invariance property of wave scattering in the disordered medium from this paper in PNAS. This is a theoretical paper which has a lot of mathematics. I want to avoid the mathematics and directly show the physical picture to you. So first I will introduce the classical theory about invariance in the diffusion random works, and then extend it into the resonant medium. Which has two aspects. One is in the resonant medium, and another is beyond the diffusion. For example, the Anderson localization. Many people discuss about this, and the final summary. First, let's see the classical theory about the diffusion random work. The movement about ants or some other particles in a surface can be modeled as a diffusion random work. For example, in this surface, we have a particle enter at some point, and it has some trajectories, and finally leave the surface, leave the box, for example. And we can define passage time about this, dwell time about this ant, about this particle. And by average the ensemble, we can get the average time about this process. And Blanco and Fourier prove that this average time is independent to the mean free path. And the mean passage length is only depend on the geometry about the system. only depend on the volume and the surface about these balls. And which is a very famous physics and has some other related aspects. For example, one may be familiar with Cat theory, which describes the mean recurrence time about this particle. The mean recurrence time is defined also, for example, in a particle, it starts from some subspace and evolve and come back and return to the initial state, initial subspace. So the mean recurrence time is a constant number. Also only depend on the volume about the environment and the volume about the subspace, which is just the start point. And it has a quantum version found by Prom, also related to microjet. The quantum version about this mean recurrence time, defining a monitored quantum work, is also a constant number. Only depend on the dimension about effective hyperspace. The dimension about it is a kind of volume defined in the quantum work.
Can you explain more what you mean by this time? This
Recurrence time?
the recurrence, recurrence time.
Yeah, we have some environment. For example, we have an environment, and the particles start from some point or some subspace. Leave from this subspace and then come back. Yeah, this is a kind of recurrence or return problem. Yeah, return problem. Yes, and by average it, we can define the mean recurrence time. It's constant number. Yeah. So the question arises: for particle, we can find the invariance about the passing time or about the recurrence time. How about the wave? Unlike particle, the wave has phase. It can interference or has some resonance and many different physics about the wave, about the light. And we all know in the wave physics, the transport process is depend heavily on the mean free path. We know that from the course. So it is a kind of conflict to the previous theory, right? The theory said it's not depend on the mean free path. So, but the authors state that the invariant time and the length can also be defined in the for the wave, for the light. But we need some corrections to the classical diffusion theory. So first, let's consider the resonant medium. We have a system with some random point scatters. For example, we have some atoms inside this system, inside this slab, and the wave enter from this side, and we have some transmission, and we have some reflect, and we have some resonant scatters inside. And we can use this dirt to define the how far about this light away from the resonance frequency. So dirt equal to 0 means the light meets the resonance about this medium.
Resonance of what?
Resonance about this scattered about this medium.
The resonance frequency of scatter, so they are all identical, all same scatter.
Yeah, same.
And they have some resonance.
Yes.
That's the mean resonance that we
Yes.
Okay.
Yeah, so delta equal to 0 means the frequency about the light meets the resonance about the particle. And you can see it kind of delay about the trajectory at the beginning. And when we far from the resonance, you can see the light just go directly through the medium. And this is the plot about the mean passage time, about the mean time for the waves. This blue line is for transmission, and this red line is for reflect. And the black line is just average about these two. So we can see the average time by verifying the delta. By varying the delta, we can see the average the mean time is a constant number, which just fit the classical diffusion theory. It only depends on the value about the slab and the surface about it. This C is the speed of light. But for the resonant, close to the resonant, this theory doesn't work. We can see the average time is not a constant number. So we need some correction. The reason why it does not behave like an average number, a constant number, is because the resonant just trap the light, the photons, and it's kind of delay, time delay, named beginner time delay. So by considering this, the definition about the mean length in the resonance media should not be the speed of light, should be a speed of energy. It's we call it energy velocity. See, this is a correction. We need to consider the resonance phenomena. So by considering this part, we redefine the time, the average, the length, the mean length about these trajectories. We can again get a constant number about this mean length, which means
Can you explain this, the black line? I don't understand what you mean by average.
Because for this process, we have some part of the light transmit and some of reflect. So you can define two time. One is transmitted time, another is the reflected time. This black line is just average of the two. Power.
That seems to be the average. If you take the sum of the
Yeah, some power. We have some prefactor. Yeah, consider for example 8% transmit and 20% reflect. Yeah, times
so
the.
you have to.
Yes.
So it's normalized?
Sorry.
It's normalized?
By consider the percent of these two physics.
You have to.
That's the first research about the paper. They consider the energy velocity and use this correction to get the invariance in the resonant medium. That's the first one. And then they consider the Anderson localization. In the region of Anderson localization, we know waves no longer diffusion through the whole value, the whole environment. They are kind of froze in a local region. So the classical diffusion theory does not work because it depends on the whole value about the system. But we know in the localization we cannot spread the whole value. So we expect this classical diffusion theory does not work. So let's see some example. We have a waveguide, and the light goes through this way and spread in the whole waveguide. So without any particles, particles inside the waveguide, it's a kind of clean waveguide. You can see also there is a black line. Black line is the average time. It's also a constant number and fits the green line. The green line is the stereo. They match very well. And for this system, we named chaotic system, which we add some particles inside the waveguide, but just a few one. For example, 10 particles inside. So it breaks the order in the waveguide. We name it a kind of weak disordered waveguide. Then you can see the wave does not just uniform as this, and has some disorder. And we can find the average time, and this also matches the theory very well. But when we consider the Anderson localization system, we have many particles inside the waveguide. So it's a strong disordered waveguide. The waves are frozen at the beginning at this area. So, and when we measure the average time, it no longer behave like the classical diffusion theory, but it's a kind of a bit lower. But we can still see a invariance, a constant number. So why? The author states the universe theory for this meantime is not only considers the geometry about the system. It should be considered the density of the state and the number of income scattering of this rho and n. It should be defined by these two quantities. The rho is the density of states. It just describes the eigenmode of the eigenmodes that are permitted to exist within a unit energy. Which means if the rho is larger, then for the photon we can have more eigenmode to stay, which means we need more time for this photon to skip. So the larger the rho, we get a larger mean time. And this n just depends on the incoming scattering channels. It just depends on the width of waveguide and the wave members. So for the three systems above, this n is the same, just the same. So the difference is only about the rho, the density of the state. Yeah. So let's say using this theory and the Wheeling laws. Wheeling law is just about how to get this density of states. With this Wheeling laws, we get this rho is dependent on the area or the volume in the 3D system and the frequency. So by considering this, we can get it convert to the classical differential theory, and it matches the theory well. But for this localization situation, we need a correction for this Wheeling law, which means because the particles inside the waveguide is very, very dense, we cannot ignore the particles inside. We have to consider the influence about the inner boundaries, the inner particles. So by considering these inner boundaries, this B, and we can get a correlation term. This correlation term makes this density kind of smaller than the classical one, because this B is very, very large. So this is smaller than the previous one. So you can get a lower theory considering this correction. That's the reason we get a lower one. So this theory just give us the source of the derivation is not because the localization makes the wave cannot spread into the interior value, but it's just because the particles is too dense. It changes the effective boundary about the system. It's a kind of, and this tells us even in the strong interference system, we can still get the average time, and it only depends on the system's geometry. But the geometry must consider the internal boundary. Yeah, that's the reason. Okay, let's do some summary. First, we know the invariance in the classical diffusive random work, and we extend it into wave, into light. And we consider two situations. One is the randomness median. We need to consider the energy universality instead of the speed of light. And in the theory, in the system of understanding localization, we still can get the invariance, but we need to consider the internal boundary. Yeah, that's all.
Thank you.
That was not easy to explain, but you did it well.
Okay.
Yeah, very good.
Thank you.
Without too many equations, it was.
Okay. Yeah, questions?
Very good.
Any question? Come on. I'm sure you have questions. So what you show is that, what they show is that whatever the regime, this time, this a kind of dwell time inside the system, is just depends just on the geometry of the system.
Yes.
Right?
Yes.
And how do you explain again? How do you define the new geometry when it's localized?
Yeah. Yeah. Let's see this figure. We have many particles inside the waveguide. So the waveguide has some boundary, right? So the new geometry considers the boundary about the inner particles. Yeah.
Right. But where it comes into the
Yeah.
So
This
what is this C and B?
Yeah. This C is the area, the boundary about this waveguide, about the environment.
You mean you count the length of the here is seen into this the length of the boundary?
Yes.
I mean geometrically.
Yes.
I already measure the.
Yes.
Okay.
Yeah, you see, the definition about C is 2D, because this is D,
Yeah.
right? The boundary is 2D. And B, you need to consider the internal. B0 is about this I about the length about this part, right? So and each length will have some density about the inner particles.
So what is B0?
B0 is some constant number, something. I don't know. You just measure it and give it.
Well, so C is 2D, so that's those boundaries, transverse boundaries.
Yeah.
And B is 2L, the other boundaries in the other direction.
Yeah, but this I think B0 is the length for one particle. Maybe this is time. I need to check it.
Okay.
Yeah, this just internal boundary about the particle inside.
So it's okay. So you said this is larger than C. B is larger than C.
Yeah, B is very large.
So it reduces the density of state.
Yeah. Yeah, this should be time. B0 is for one particle.
And so on.
Yes.
But why L and D does not come into the picture for the chaotic case or the
Yeah,
basic
because
case?
for this chaotic case,
Why don't you need?
we just have a few particles. So internal contribution is very, very small. So we don't need the correction about this.
But the L and the D, this is not the particles. This is just the
Yeah,
waveguide itself. For the waveguide is the same for all the three cases.
yeah. For C, all the cases are same, but for B is different. For B, in this case is 0. In this case, very, very small. It's
Why it is 0? It's 2L? No, it should be 2L. Why B is not 2L for the first?
Yeah, 2L. B0 is is a contributed term. 2L compared to C is very, very small. It's nearly to B0.
Okay.
Yeah. Just because this B0 is large. Yeah. L and D are just a constant number.
And can you say something about this relation that the mean time is related to the density of state?
Yeah. This is just by solving the Helmholtz equation. Yeah. By solving this, and you can describe a kind of some time operator, some time delay operator, and by solving the eigen energy, eigenmodes about this, you can define that. Very, very complicated mathematics. I don't fully understand it. I just know the result, conclusion is this. Yeah. You want me to explain what is rho and
No, that's my question. Are you going to T, average T, and rho?
Yeah. So the question is to explain what is rho.
Yeah, no, rho I understand, right? So that's the density of state, right?
Yeah.
So let's say in the localized regime,
Yeah.
rho should be small, right?
Yeah. Yes.
So the mean time should be smaller, right?
Yes.
But
Yes.
it's not. It should be actually in the localized regime. It should be larger than.
Yeah,
it should be
that's
long. You stay long time inside.
Yeah, that's the reason about this because, in my understanding, the effective space about this light to involve is reduced because we have many particles inside. So the wave with the particle is just cancelled. It cannot be involved into the particle, this area. So the area is reduced by the particles. So the effective surface, effective volume about this light is just lower than the previous one. So the mean time should be lower. That's the explanation. Yeah, just reduce.
No, so that's okay. So 2 is smaller. Okay, well, that's fine.
Okay.
But I would assume that the average time spent in the strongly scattering medium should be larger than in the ballistic or slightly diffusive system, no? Maybe I don't understand very well what is this average T, what I mean by mean time. What is this mean time? Maybe you can explain again what they mean by mean time.
Yeah, mean time is for one photon, it has trajectory, it can be transmit this waveguide or reflect. As maybe they consider the reflect is much larger, it's smaller, the reflect. Maybe this is one explanation. Yeah. The mean time is just defined as this. The light goes through, we have some time, and or reflect, we have a time, and we average every samples.
Yeah, you have to take the average between transmission and reflection.
Yeah.
And when you are localized, reflection is huge.
Yeah, but reflect may be smaller. Maybe.
Transmission is small, but reflection is strong.
Yeah, I think transmission is strong, but the reflection could be smaller.
In the localization regime?
Yes, they don't so see that, but my understanding maybe this.
No, in localized regime, if you are not at resonance at a localized state,
Yeah.
then most of the energy is just reflected back.
Yeah.
You don't have transmission.
Yeah. So the reflex time should be smaller. The time.
The time, right.
Yeah,
So
the time.
the corresponding temperature is
Yeah. So this is lower because it's averaged by all everything.
Okay, very nice.
Wow. Thank you. Any questions?
Thanks a lot. So, do we make a break?
Another one?
Or you want to
How many people there is?
Two.
You and
No. Only you?
Only me?
Yeah,
Okay.
yes, sir.
Let's do it.
Let's do it, yeah.
I'm working this really hard. And I really enjoy it. Really.
Just
But
need
now-
to be
It's too much stress for me. I have a problem with chest. Like,
Just 1 minute, I come back.
אוקיי. מישהו יכול לעזור לי לכבות את המחשב ולתת לי נבוט בראש? וואי, מה זה קשה?
אני יכול לתת לך
קשות לי הסיטואציות האלה. It was very good.
Thank you. Yeah, good luck to your child.
Thank you. I'm too stressful.
Yeah, just
I'm not doing good at tests.
No one can do that. Just yeah.
Dat is ook goed.
You make it there also.
לא משנה. נראה לי
这个家
להסתכל.
是我的
נראה לי
都有
להסתכל. יש לי חיבור ישיר.
给我买个扫地机器，
在这边吗？
就是给我妈做生日，但
咖啡
是
很难选。
是的，
אני פשוט אעשה
追
מה?
觅石头
其他的她都有。
啊，可以，我觉得可以搞一个。
追觅我给广告打出去，我担心有溢价。
就是我知道的肯定都是
אתה יודע מה זה סמארט?
כלום, אין דבר כזה.
这我感觉我逼着好多 UP 主都打过这个。
还有石头也是。
石头，
ואיך אני משנה את ההגדרה שכאילו זה יקרין את ה-USB?
有别人说是。
זה את המחשב ואת ה...
לא, אני אעשה את המחשב. אבל חיברתי את זה
有
כאן
点一样，让你接受，就别太夸张。
אתה רוצה להציג מפה או מפה?
看的
להציג
就是
מהלפטופ
最
או
新
מהמחשב
款
נייח?，
要3000。
אם אני
然
רוצה
后
להשתמש
旧
בשבת
款
אני
的
חייבת
话，
מחשב
大
נייח?
概1年前的有2000，
אז אני אשתמש במחשב.
但是我觉得
שיהיה לי יותר...
现在买的有点贵，别人跟我说就最新款是3000，
过年可能就没打折。
就现在这个过年。
我觉得旧款和新款有什么区别？这东西都出来多少年了？这东西出来得50年了，我觉得
就是更稍微更
方面
高级一点。
אוקיי, ממש קורה משהו.
很难选，你很难找到一个不是广告的视频。
Okay. Okay. No, he's not here.
So you can command your PowerPoint with the phone.
Oh,
Sorry?
how can I do it? Like through here?
How did you
My phone.
yeah, but
Ah, okay.
Because this is Mac. It's Apple.
because it's Apple.
Yeah.
So I'll do it from here. Okay, so before we start, I want you to describe something. I want you to imagine there is a big block of aluminum sitting right over here. So what are your thoughts? I mean, there is nothing here.
So to get started from
Okay. Yes, yes. So I want you to imagine something like there is a big block of aluminum just sitting here. So for the naked eyes, there is nothing here. He's quiet, still. I mean, what can possibly be here? So in physics, I want you to understand that there is so many noise inside. The phonons, the thermal energy inside, the particles that are moving. This is a truly symphony to our ears. Ta-ta! Okay, so this article is based on the paper by Weber and Lokis, okay? I'm just gonna say something. This is really and extremely interesting. I really enjoyed doing this, so bear with me. I know I'm the last one, but just bear with me. Okay, so the big question, can we imagine a medium without using an active source? I mean, we know from so many physics inventions that if we want to see something, the path of the waves going through a solid body, we need to pulse it. We need to put an active energy in the system, an active source of something. Okay, like in ultrasound, we have waves coming inside our stomach, like as a pregnant woman, heating the baby inside, and then we can acknowledge the space inside, like how close his leg is to his head and something like that, and to get a picture of the path that the waves come through this body. But for that, we need an active source of energy. So the concept, traditionally diffuse fields, like random noise, were thought to be devoid of phase information, and I will describe this later because the phase information is so important, super important. So the breakthrough, which Weber and Lokis did, is that using cross correlation, they extract deterministic information with Green's function, which I will discuss this too, from poorly random ambitious noise. So before we get to all of the theory, let's go through some key terminology, some subjects, so everybody will know everything before. So diffuse field. I want to show you the next one. You know what? No. Okay, so in diffuse field, you already know it. There is a multiple scattering. Okay, there is so many mass. It looks like garbage when waves is coming. You scatter back and forth, back and forth. We don't know where the wave came from, where he is going through. We don't know his path. Okay, so this is the diffuse field. The Green's function is the impulse of a response of a system, like pulse of energy, and how the energy in area X is affecting the area in Y point. We need to have an extremely impulsive energy, and we have the Green function for it, and I will discuss this later because this is very important as well. Thermal phonons. So you already know it from quantum or mechanics. These are particles that are moving together. Like there are a lot of modes. Each mode has a different frequency, and each mode, all of the particles are moving in the same rhythm, to the same direction, like in a little bit of harmony. The transductor is a device that converts a mechanism, a vibration, into electrical signal. Okay, זה מתמרים in Hebrew. מתמרים, ממירים. Cross correlation is a mathematical operation that measures the similarity between two signals as a function of time lag between them, and the impulse, you already know it, it's a delta function. Okay, so the coherent pulse versus the diffused one. So let's discuss about the focused pulse. This is a well-defined wave packet traveling in predictable path. We know where he came through, where he's going through. We have his green function. We know everything about him. We know his energy, the timing, the phase. For example, setting a high voltage, and this is his pros. The SNR ratios, the clear timing, as I said, directly reveals the green function. We know the green function, the green function for the focused pulse. So now let's see the diffused one. Before that, I want to discuss the importance of the green function. Okay? So the green function really is the system's DNA. It tells us how the medium is shaped. Think about waves that are returning and scattered. We can know where are the boundaries of the solid. Like if there is an aluminum or something, we can know his boundaries, the phase, the timing. Of course, the energy, the density of the medium. This is our DNA. This is where we start. This is our mother base. If we have the green function, we know most of the thing about the medium where we are sending our waves. Okay? So let's see the function itself. So L, it's the operator. Okay? It's the wave operator. Like for example, the waves operator. The green function, delta, the X and the Y are two separated locations, which could be the transducers. Okay, it can be one receiver and one the source, and the opposite. Okay, and when the source is equal to the receiver, we get the peak. Okay. Everything. So this is also the properties: the speed of the wave, elasticity, the density of the medium. I already said. So now let's go again for the diffused one. Okay, so the diffused field. This is our questions, I guess. It's wave that scattered so many times. It looks like a mess, but let me tell you something. There is a lot of data inside still. I think that's it. I don't want to repeat things I've already said. And the example is again the phonons is the natural thermal vibration you have in the material. It's something that already exists. You don't have to put energy to notice it, to notice this kind of motion and this kind of energy. Okay, so the old belief is that scientists thought that once the field becomes diffused, all of the phase information is lost. And the importance of the phase is that this is the clock of the wave. It tells us the exact position and timing. If the phase is lost, we lost the ability to measure the distance and time of flight. And the big question is, can we get an active quality result from passive noise? Like, can we get the same result? Can we get the greenest function even when speaking about the passive noise and not the active noise? So let's start. Before we get to the experiment that Weber did with the aluminum, let's start from the beginning. Before you start doing things in the lab, you want to see mathematically if you have a base for this theory. You want to see if the numbers are at your side. So the mathematical foundation start at in this function, which this is a diffused field of bounded body. There are boundaries, and it starts from the real part of the summation of all of the different modes inside, and this is the amplitude. Okay. So this is the noise we get at the end of this article. This is what we are looking for. This is the summation. This is the real part because, again, this is physics. We measure it. It's supposed to be at the end of the week. Something real for us to measure. This is our psi. This is the wave function, the mode shape. This one is the amplitude after scattering, like the height and the volume of it. And this is for the oscillation. After you do the real part, you get the cosinus, the cos from it. Okay, so in our experiment, I told you there is a big aluminum block. There are 2 sensors, okay? And if we want to see the relationship between those 2 points, like if one is a source and the other one is the receiver or the opposite, we want to see the multiple between them in a tau amount of time, okay? And then we integral the whole space, okay? And we get this equation. And from orthogonals, this expression is equal to delta, which is 0 if n is not equal to m, and equals to 1 when n equal to m, from our orthogonal. And this is what we get at the end. Okay, this is the result. This is the relationship between the 2 sensors. Okay. I wanted to add something cool. Okay, I wanted to ask you if maybe this looks familiar. The equation, this one, maybe. No, that's fine. That's totally cool. Is somebody heard about the Calendic figures? That's fine. Okay. Yes.
Waves, yeah.
Cool. Amazing.
Yeah,
I will explain. So this here is the sand, and then somebody, like a violin, play a specific frequency that makes the sand on top of this place goes into shapes. Okay, there are some spaces that there is no sand, there isn't at all, but they are moving and then creating this shape. And each shape here, it's a different frequency. Okay, and the cool thing about it, and I will touch it in a minute in our experiment, is that here it's like the speed is very high where you don't have sand, but where you have sand, it's like modes, like כאילו גל עומד in Hebrew, where the speed here equals to 0. Okay. And remember this because in the graph I will show you how the graph of the experiment looks like, and then you will do the connection. Okay, so we got this equation just a minute before, and here I wrote the acoustic green function for a pulse. Okay, this one is a pulse. This one is a passive wave. Okay, you can see really directly that they have a defined relationship between them, between the active one and the pulse and the passive one, which comes in the derivative or the statistical correlation equal of the Green's function of the active one. Okay, so they really do have a defined relationship between them. So we really do succeeded on finding that even a passive noise has a Green function. Like we can see the data. We can locate his Green function from the experiment, and mathematically we can see it. We can see it over here. So mathematically proved. Now let's go to what Weber did.
It's proof or this is just an observation? So we observe.
This is what the mathematical what we proved right now. This one, and this is also כאילו מהספרות, כאילו זה קיים, זה מה שהם רשמו גם בארטיקל. This is an existing acoustic Green function for a pulse one. Okay, so this is the experiment setup. So this is an aluminum base. There are two sensors.
So this is the box.
This is the box. This is the box. Okay, and there is also another sensor to boost the signal, because the passive noise is so, like, of course we can't hear it, of course, but even the greatest sensor don't always hear them, so we have to have something to boost the signal, the quality of the sound, and it has to be very good, because we don't want it to overpower the signal, like the passive noise itself. So even the boost one cannot be that noisy, because then all of the experiments can go to the garbage. Okay, so in this experiment they showed two waves, okay? So for each kind of wave, so for the passive one and for the active one, for the pulse, okay? For each of them, they showed two waves, okay? The one is the autocorrelation, okay? And the other one is the cross-correlation. So the autocorrelation is a signal, like the delta function that I show you. There is an x and y and minus y. So when we are talking about the autocorrelation, I'm sorry, I'm gonna move on. We are talking about when the source is also the receiver. When the sensor itself, he sends a signal, like the active one, okay? He sends a signal, but then he also listens to it in the same sensor, okay? So all of the waves that are coming back to this sensor that was before the source, is now is also the receiver, are the echoes, the waves that came back to this sensor. Okay, so this is in the pulse, in the active wave. Okay? And the cross-correlation, this is really is the experiment that we can see both the passive and the active, is when x doesn't equals to y. What does it mean? That there are two sensors and the waves are coming through both of them, okay? So in the active one, the x is sending a signal and the y is the receiver, and the passive one, there isn't any active or pulse. They are listening to the noise, to the thermal noise, and all of the waves that are coming through both of those points are recorded. Okay, and I will show you how the correlation is working, because the correlation is the most important part here, because the thing is that I don't want all of the noise inside my system. There are too many waves in the passive one, too many waves, too many scattering, too many noise that it's not really that I don't really need. Okay, so what I do need is all of the waves that are coming through those specific points, but in time difference that equals to tau, okay? And it's also based on a statistical way, because we have to do this experiment multiple times and then to see a really pattern, like a pattern of the waves that are really we are interested in them. It doesn't work if you do it only once or twice. You need to do it hundreds of times, and then you can see really what you want to see. So this was for the active measurement. In the passive measurement, we have the autocorrelation, which I already told you. It's processing the noise only in one location, in X. And the cross-correlation is processing the noise between two separated transducers. I'm sorry. Okay, so now for the keys findings. This was the graph that Weber discovered. Okay, the top one is the cross-correlation of the active one. Okay.
Autocorrelation. Noise autocorrelation. No. It's written autocorrelation, not cross-correlation.
Yes, I'm sorry. Yes, what I was trying to say is this one is the active one,
Yes.
is the pulse one. This one, what to say, and this one is the passive one. Okay, and shocking, it looks very similar. Okay, both of the graphs have the same peaks here, 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 here. Even the quiet areas, which I'll talk about, are happening at the same places. Okay, so we really do see a lot of similarity between the passive and the active one. So we do succeeded. And now for the peaks. The peaks is where the wave was returning after scattering the boundaries. Okay, and the quiet areas is where all of the waves where there isn't a wave coming through the two sensors. Okay, it means that they didn't went through those sensors between X and Y. Okay, or that the phases limited each other, which we couldn't see them. So this is the quiet areas. So this is also exactly what happened here, the quiet places. Okay? The quiet places and the peaks. Which bring me to constructive interface. So it's all related to the phase, because I told you that in the quiet areas, the waves had a different phase, okay, which was destructive, okay, and the highest peak they had the constructive interface, okay. So here you already know all of this material, and so the constructive interface occurred. I'll show you in the graph. All of the constructive is here. It doesn't have to be the highest peak. Just having the information is also constructive, but in different phase. It means the difference in the phase was very, very little. Here it was 0. Okay? And here, the quiet area, the difference in the phase, could not obtain this equation, okay? Because in order to have the constructive interface, this is the amount of time between X and Y, okay? So if it's not a whole multiplication of T, it means it's going to be a destructive one, okay? So tau is like, again. There is X and Y, so the times for a straight line to go through X and Y is tau, okay? So as long as there is a whole multiplication of n, like 0, 1, 2, 3 of t, it's fine and it's constructive. But if it's not, it's 0, and then you will see the quiet places. Okay, so something a little bit philosophic now. Sometimes the most profound answers are found not by shouting at the world, but by listening carefully to its silence. And I think this article is very important, and we can see this sentence coming to life. Because we don't need to shout at the world. We don't need to have an active pulse full of energy into our system to understand the medium. We can just listen to the medium and get all of the information we want, the green function, just by understanding it. And why it is important? Why what Weber discovered is important? Because sometimes you can't put energy into your system because you don't want to. Sometimes it's too risky to add energy or heat into our organs and some sort of the thing, or into airplanes, or if you have an earthquake, if you want to prevent an earthquake and learn more about the land, instead of using a dynamite and go through the earth, you can just listen to the waves, to the ocean, and then get all of your information. You don't have to get a pulse. You don't have to put a dynamite energy or something. You can just listen. So in seismography, what I just told you about the earthquake, this is very relevant. Or if you have an airplane and you want to know if he's well built, so you listen to the metal and understand if he's fine and ready to fly. Thank you.
So what you said at the end, those are applications. This method is used in application. Did you find some article related to that?
Yes, so the earthquake, like the one with seismography, I did find an article speaking about this, so it was amazing. And then something with airplanes, but not a whole particle, not a whole article. I searched through Google and sorted answers because I wanted to understand why was it so important to understand it. If it really is a breakthrough in physics. I mean, it's very cool to understand that, but I wanted to do it.
Sometimes you cannot put a source somewhere, or so you can just listen to the noise, and that's enough.
Yes. It was really very interesting. Like the first time I read this, what am I reading? But then I discovered it, and I really enjoyed it. And I'm so sorry for my English. In Hebrew, it will be much better because I have the whole vocabulary in physics.
That's part of the exercise. That's good. It's part of the exercise.
Yes.
Any question? Okay. Okay, thanks a lot.
Thank you so much. Thank you for everything.
Okay. I want to thank you all because we had really a great time today and last week also. It was really, I'm very impressed by the presentation and by the group also. I mean, during all the course, I had a lot of interaction with you, and it was really a pleasure. It's not always like that, and